The ideal gas law is the equation of state of a hypothetical ideal gas. It is a good approximation to the behavior of many gases under many conditions, although it has several limitations. It was first stated by Émile Clapeyron in 1834 as a combination of Boyle's law, Charles's law and Avogadro's law. The ideal gas law is often written as, where the letters denote pressure, volume, amount, ideal gas constant, and temperature of the gas, respectively. It can also be derived microscopically from kinetic theory, as was achieved by August Kronig in 1856 and Rudolf Clausius in 1857. Equation. The state of an amount of gas is determined by its pressure, volume, and temperature. The modern form of the equation relates these simply in two main forms. The temperature used in the equation of state is an absolute temperature. In the SI system of units, Kelvin. Common form. The most frequently introduced form is where P is the pressure of the gas, V is the volume of the gas, N is the amount of substance of gas, R is the ideal, or universal, gas constant, equal to the product of the Boltzmann constant and the Avogadro constant. T is the temperature of the gas in SI units, P is measured in pascals, V is measured in cubic meters, N is measured in moles, and T in Kelvin. R has the value 8.314 Jk-1 mol-1 or 0.08206 LATM mol-1 K-1 or 2 calories if using pressure in standard atmospheres instead of pascals, and volume in liters instead of cubic meters. Molar form. How much gas is present could be specified by giving the mass instead of the chemical amount of gas. Therefore, an alternative form of the ideal gas law may be useful. The chemical amount is equal to the mass divided by the molar mass. By replacing N with m, and subsequently introducing density ρ equals mv, we get, defining the specific gas constant R specific as the ratio R, m. This form of the ideal gas law is very useful because it links pressure, density, and temperature in a unique formula independent of the quantity of the considered gas. Alternatively, the law may be written in terms of the specific volume V, the reciprocal of density, as it is common, especially in engineering applications, to represent the specific gas constant by the symbol R. In such cases, the universal gas constant is usually given a different symbol such as R to distinguish it. In any case, the context or units of the gas constant should make it clear as to whether the universal or specific gas constant is being referred to. Statistical mechanics. In statistical mechanics, the following molecular equation is derived from first principles, where P is the absolute pressure of the gas measured in pascals, N is the number of molecules in the given volume 5. The number density is given by the ratio N, V, Kb is the Boltzmann constant relating temperature and energy, and T is the absolute temperature. The number density contrasts to the other formulation, which uses N, the number of moles, and V, the volume. This relation implies that R equals NaKb, where R is Avogadro's constant, and the consistency of this result with experiment is a good check on the principles of statistical mechanics. From this we can notice that for an average particle mass of μ times the atomic mass constant μ, and since ρ equals Minnesota, we find that the ideal gas law can be rewritten as, in SI units, P is measured in pascals, V in cubic meters, Y is a dimensionless number, and T in Kelvin. K has the value 1.3810-23 Jk-1 in SI units. Applications to thermodynamic processes. The table below essentially simplifies the ideal gas equation for a particular processes, thus making this equation easier to solve using numerical methods. A thermodynamic process is defined as a system that moves from state 1 to state 2, where the state number is denoted by subscript, as shown in the first column of the table. Basic thermodynamic processes are defined such that one of the gas properties is constant throughout the process. For a given thermodynamics process, in order to specify the extent of a particular process, one of the properties ratios must be specified. Also, the property for which the ratio is known must be distinct from the property held constant in the previous column. In the final three columns, the properties at state 2 can be calculated from the properties at state 1 using the equations listed. A. In an isentropic processed system, entropy is constant. Under these conditions, P1 V1 gamma equals P2 V2 gamma, where gamma is defined as the heat capacity ratio, which is constant for a calorifically perfect gas. The value used for gamma is typically 1.4 for diatomic gases like nitrogen and oxygen. Also, gamma is typically 1.6 for monatomic gases like the noble gases helium and argon. In internal combustion engines, gamma varies between 1.35 and 1.15, depending on constitution gases and temperature. Deviations from ideal behavior of real gases. The equation of state given here applies only to an ideal gas, or as an approximation to a real gas that behaves sufficiently like an ideal gas. There are in fact many different forms of the equation of state. Since the ideal gas law neglects both molecular size and intermolecular attractions, it is most accurate for monatomic gases at high temperatures and low pressures. The neglect of molecular size becomes less important for lower densities, i.e., for larger volumes at lower pressures, because the average distance between adjacent molecules becomes much larger than the molecular size. The relative importance of intermolecular attractions diminishes with increasing thermal kinetic energy, i.e., with increasing temperatures. More detailed equations of state, such as the van der Waals equation, account for deviations from ideality caused by molecular size and intermolecular forces. A residual property is defined as the difference between a real gas property and an ideal gas property, both considered at the same pressure, temperature, and composition. Derivations. Empirical. The ideal gas law can be derived from combining two empirical gas laws, the combined gas law and Avogadro's law. The combined gas law state that where C is a constant which is directly proportional to the amount of gas, N, the proportionality factor is the universal gas constant, R, i.e., C equals near. Hence the ideal gas law. Theoretical kinetic theory. The ideal gas law can also be derived from first principles using the kinetic theory of gases, in which several simplifying assumptions are made, chief among which are that the molecules, or atoms, of the gas are point masses, possessing mass but no significant volume, and undergo only elastic collisions with each other and the sides of the container, in which both linear momentum and kinetic energy are conserved. Statistical mechanics. Let Q equals and P equals denote the position vector and momentum vector of a particle of an ideal gas, respectively. Let F denote the net force on that particle. Then the time averaged potential energy of the particle is, where the first equality is Newton's second law, and the second line uses Hamilton's equations and the equipartition theorem. Summing over a system of n particles yields by Newton's third law and the ideal gas assumption. The net force of the system is the force applied by the walls of the container, and this force is given by the pressure P of the gas. Hence where ds is the infinitesimal area element along the walls of the container. Since the divergence of the position vector Q is the divergence theorem implies that where dV is an infinitesimal volume within the container and V is the total volume of the container. Putting these equalities together yields which immediately implies the ideal gas law for n particles, where n equals n, Na is the number of moles of gas and R equals NaKB is the gas constant.